are bridges on life's highway, but we never see them there. Some cross troubled waters, some don't go.
This is part 2 of a 2-part documentary about the Collmog Bridge in Otaki. Sadly, this is a bad bridge, a bridge that has prevented Gary and Lynn Hirtanen from fulfilling their dreams since 1998. Last time in part 1, we learnt a little about Gary and Lynn and their plans that have been thwarted by the bad bridge for the last 17 years. Then we looked at the New Zealand Bridge Manual and its role in bridge building. Producer statements are an integral part of the design and building process for a bridge, so we learnt about them too. And finally, Stuart, our bridge builder, helped us to build an imaginary good bridge that would do the same job as the bad one, so we could see how it should be done properly by a professional. Let us quickly go back to part 1 and refresh our memories. Imagine it is 1998 and you have just purchased a beautiful piece of rural land in Otaki, which is accessed by a bridge. All is well, until in the early 2000s you find that the bridge is unsafe. Now, imagine that we jump ahead from 2000 to 2015, and the bridge is still unusable and unsafe. And what is more, you have since discovered that the bridge has never been safe, and in fact should never have been built, let alone given its council approval as being a safe structure. Sadly, for Gary and Lynn Hirtanen, no imagination is required, because the bad bridge we are looking at is the bad bridge to their paradise. And yes, after 15 years, they still do not have access to their land. In the late 1990s, when Gary and Lynn bought their new section, they were shown the council approvals and paperwork that said the bridge had been designed and built properly, was inspected by the council, and was safe. Further, they had no reason to suspect that there was or would be any issues with the bridge that led to their new property. It should also be kept in mind that Gary and Lynn had nothing to do with the design or construction of the bridge, and they do not own the bridge nor the land it is on. In law, they have no more responsibility for the bridge leading to their property than a Waikanai resident has for the bridge on State Highway 1 leading to Waikanai. Gary and Lynn Hirtanen.
Yeah, we wanted to, and we left England with this in mind, that we wanted to live where it was self-sustainable.
Well, we would be basically, in our minds now, living in a very nice straw bale house, and we would have 6 to 8 whares, a library, all interlinked paths, our own hydro system, self-sufficient gardens, hopefully have a very nice, comfortable business and a beautiful place to live.
We've just been completely unable to do that.
Gary's whole property purchase was based on the fact that this structure was code compliant. It was an illegal structure at the start. It never complied. It does not comply. The structure needs to be torn out and replaced.
The first alarm bell that should be ringing is if there's no building consent, what is the quality of the work?
And then this is the underside of the...
What a mess. Heavens above.
And so from a coatings perspective, is it fair to say complete disaster?
Absolutely. Although I don't think we should hold coatings in too poor a regard, because it seems to me there was very little coating on it when it went in there.
The council should have had alarm bells screaming with this bridge.
That was Stuart Quigley of Quigley Farm Bridges, who has been building bridges for a living for the last 25 years. John Scurry, a structural engineer based in Auckland, and Mick Morris, whose experience in corrosion protection coatings spans 20 years and is worldwide. We will also be joined by Willie Mandino of Opus International, who is a world-renowned corrosion expert. Stuart, John, Mick and Willie will be helping us try and understand the bad bridge during the rest of the program. Having built our good bridge in part 1, in this program we are going to examine the bad bridge while trying to keep as closely as we can to the process that we used for the good bridge. Thus, we will use the producer statement system as a methodology for trying to understand the bad bridge. But as you will see later on, This is problematic because the bad bridge did not follow the standard processes. Why did we build an imaginary bridge in part 1? Simple. The purpose of this documentary is to try and understand what went wrong with the bad bridge, and why after 17 years it is still preventing Gary and Lynn from the simple act of going to their paradise. To learn about a bad bridge, you really need to learn about a good one first, so that you have a baseline for comparison. This program was created with support from Gary and Lynn Hurtanon, Stuart Quigley of Quigley Farm Bridges, Willie Mandino from Opus International, Donald Cicaldi, formerly of Opus International, Mick Morris from Zynga, John Scari, an Auckland-based structural engineer. It was produced by Jack Penman. Before we get started, a few notes about this program. First, if you are listening to this and you have not already heard Part 1, it would be a good idea to stop now and listen to Part 1. Second, there is a YouTube version of this program on the internet. The YouTube version is the same, except that you will be able to see the various pictures we are looking at in the program. If you are listening to this on the radio, you're fine. You can view the YouTube version later by searching Google using the term The Bad Bridge to Paradise. For the remainder of this program, we're going to learn about corrosion in steel, find out how steel can be protected from corrosion. Then Stuart and I are going to sit under the bad bridge and look at how it was built and what some of its problems are. And finally, we will look at the course of events that not only enabled the bad bridge to come into existence, but also those that have resulted in it still being a problem today.
Rusty, may I call you Rusty?
Corrosion. Before we can appreciate the bad bridge, we first need to learn about corrosion, or rust. And to help us learn more is Willie Mandino. What actually is rust? What is corrosion in steel?
Corrosion is releasing the energy that's stored in the steels.
Just to make sure I've got this right, so basically corrosion is just a very slow way of releasing the energy that went into creating the steel in the first place.
Exactly right, and the same with most metals that have been refined from their natural state. So the so-called noble metals of gold and silver and platinum, they don't have any sort of stored energy, so they tend not to corrode or sort.
Because they were very easy to make, I guess.
Yes. Yeah, well, that's why they use iron filings and aluminium filings and so on in fireworks. There's a lot of energy in aluminium in particular, which is why it's used in flares and why some of those Navy ships in the Falklands literally went up like a skyrocket.
And it's for bridges. What is the most common type of steel used for bridges? And in bridges, I mean kind of small ones, about 20 metres, 25 metres, something like that.
Well, generally the size of the bridge is not too relevant, although for very large spans, to reduce weight, they tend to use what are called the higher tensile. But most of steel fabrication is done with a general purpose grade of steel that has a tensile strength of about 250 megapascals. 300, 350, 450 megapascal steel is also relatively common. It's more expensive, but it's stronger.
So rust is basically the process by which steel reduces back down to its original raw materials over a long period of time. And consequently, the energy that originally went into the making of the steel is also released, albeit very slowly. The chemical reaction between the iron and the oxygen occurs in the presence of water, which is why if you keep steel perfectly dry, it will not rust. And likewise, we all know what happens when you do not protect steel from water. So now that we know what corrosion is, the next thing we need to determine is how fast it develops. Or in other words, how quickly will it make our steel disappear? Now, in terms of the speed of rust, I know that when you look at a bit of rust in the car, and it seems to be quite quick, but in reality, how fast is rust? Is it something that goes very quickly, or is it a very slow reaction?
Essentially, it depends on the excess of moisture and oxygen. So
if we went from two extremes, so if we went, first of all, in the middle of a desert where there's pretty much no humidity, not very much moisture around at all, presumably that would be the slowest possible rate of rust?
Yes.
So at the other end of the scale, let's say for argument's sake, if we had a 10 millimetre piece of normal steel, In the desert, it's pretty much safe. It's not really going to corrode at all. If we took that same sheet and we left it, say, right next to the beach, how fast would the corrosion be in that situation, just for an average?
Well, a very rough order of magnitude number for next to a surf beach, the steel corrodes at about 0.1 of a millimetre per year. So to get down to half its thickness, remembering that it'll be corroding from both sides, that would take you about 25 years, but that's assuming it's uniform corrosion.
So
what tends to happen with salt is you get pitting corrosion, and that can occur locally up to 3 times faster, so you could get locally half the thickness in 8 to 10 years.
So if you were in the middle of our scale and, say, just next to a river and away from the ocean or away from the sea, what would the rate be like then for our 10mm piece of steel? Is it a similar rate?
Well, no, it declines very quickly. You only have to be a few kilometres inland for corrosion rates to be almost a tenth of what they'll be next to a surf beach. It really depends on topography and wind speeds. Mm-hmm. The other thing that affects it is what we call the time of wetness, how much you get dew and condensation, because it requires moisture for corrosion to occur. So anywhere that stays damp, corrosion will occur more quickly.
So on our scale, basically right next to the ocean is about 0.1 of a millimetre per year next to the sea.
Yep.
In the river, it's about a tenth of that, so about 0.01. And then in the desert, it's pretty much zero. You'd have to wait an awfully long time.
Yes. Well, remember that the corrosion is releasing the energy that's stored in the steel, so high tensile steels tend to corrode more rapidly. Where steel has been worked, say at bends or wells or cut edges, you often find corrosion occurring preferentially in those places.
We know that the Bad Bridge is located more than 10 kilometres from the sea, so salt corrosion should not be an issue. It is 14 metres above a stream, which in terms of our scale puts it in the middle. Thus you could expect the average steel loss for unprotected steel on the bridge to be about 0.01 millimetres per year. As Willie said, you can have localised corrosion taking place at a much faster rate. So going back to our 10mm section of steel, we concluded that under the worst possible conditions, on our scale that was next to the sea, it would take around 25 years for the steel to be reduced by half or down to a thickness of 5mm. For the Bad Bridge, this translates to about 250 years. This is because the bridge is far away from the sea and the rate falls to 0.01 millimetres per year. Put another way, on average we would expect an exposed section of the Bad Bridge with no corrosion protection and no debris in contact with it would degrade at an average rate of about 0.01 millimetres per year. And it would take about 100 years on average to lose 1 millimetre of steel. Why are we so interested in rust and the rate at which it develops? Simple. The Bad Bridge is full of it, as you will soon see. Corrosion prevention. Now that we know what rust is and how quickly it can damage unprotected steel, we need to learn how you go about protecting steel. Mick Morris is going to show us how to protect steel from the elements using protective coatings. If you were going to protect a bridge with, say, a 20-metre span and it was 10 kilometres away from the coast, 14 metres above essentially a small stream, just using the best practice at the time, just take me through that process. How would you have done it? If it was sitting in your workshop and they said, protect this for me, how would your company have done that?
Well, we probably need to go back a step, really, to look at the need for the bridge in the first place and how it's intended to be utilised.
And that's important for the kind of coating that you would put onto it?
Yes, it is.
Okay, great. So what would we look at?
For instance, with a bridge that's going to have a lot of cattle over it, and particularly if they're going to be panicked, there could be urine and other matter from the cattle that will affect the bridge. There are a whole bunch of things. The owners may want a particular colour
To make it blend in with the environment,
exactly
perhaps.
So,
Okay.
Rail bridges have massive loads and they flex a lot. Once the need and utility of the bridge had been established, it would then be relatively easy to choose a coating system for it. And in 1998, more often than not, it would be a high-build epoxy coating system specified to be applied in various thicknesses, beginning with a primer, a build coat and a top coat at least. You may even have 4 coats and you may have some sealer or whatever else. But basically, my expectation would be that they'd be putting on a zinc-rich primer and they'd be putting 2 build coats over that. They'd expect in most circumstances to get 20, 25 years.
Thus, if we apply the correct coatings properly, we should expect to get at least 25 years of protection from them. It is also interesting to note that each coating is usually a different colour, so that it is easier to detect scratches or other damage to the paintwork. If you can see more than one colour, you have a problem. Now that we have learnt about rust and its prevention, it is time for us to finally go down to the bad bridge.
If you go down to the bridge today, you're sure of a big surprise. If you go down to the bridge today, you'll never believe your eyes.
Picnic time for teddy bears. The little teddy bears are having a lovely time today. Watch them, catch them unawares, and see them.
One afternoon, Stuart Quigley and I spent a few hours sitting under the bad bridge, which is why whenever you hear Stuart and I speaking, there is always the sound of the stream in the background. First, we looked at how one would go about making a good bridge, which we did last week. Now, we are looking at the bad bridge, and where better than to start than the ground beneath us. To give you an idea, we're basically standing at the end of the bridge where there's a concrete wall, as it were, and Stuart, to his right, is actually a wee cliff, and he's standing in essentially the middle of the bridge. So, given that the foundation is actually probably the most important part, describe this for me.
All right, well, I'm not a geotechnical engineer.
And neither am I.
However, I can tell you that the material we're standing on is not grey-wacky. It is what we call soft brown rock.
And what is a soft brown rock?
It's basically a siltstone formed from the earth. You get the first layer under your clay, which has got the pressure of it where it's consolidated, and it's a harder material that breaks down very easily. Below that you get your hard browns, which you need to put rippers into to tear up, and below that you'll find your grey-wacky.
So just to visualise this, if we imagine a table sitting in a big trough of water. Now, the 4 legs of the table represent the abutments of the table. The top of the table represents the bridge, and the water is the soil. If the legs of the table are sitting on a firm standing, and the water represents the soil, you should actually, in theory, be able to drain out all of the water, or in this case, remove all of the surrounding soil, and the bridge will still be standing on its foundations, and it will still be stable. Is that correct?
That's correct.
So basically, everything that I'm looking at around me is basically irrelevant to the structural integrity of the bridge.
That's correct.
So tell me, what is holding this bridge up? What is actually holding us up?
The grace of God at the moment, because there's nothing much under that foundation there. The bank has crumbled, and when you look under there, there is fractured brown rock, which realistically a slight earth tremor could cause a whole lot to go.
And looking straight ahead of me, I can see a corrugated iron sheet, and I think behind that there's some concrete. Now, if you were building this bridge, I'm standing right in front of a relatively new metal beam. Should I be able to stand here, or should there be some kind of concrete here? How would you support this so that it's safe?
this bridge in this situation should have bored concrete piles where you would bore down through the soft brown material till you established you were into greywacke. You would bore into that until you got a sufficient depth in with a sufficient number of piles to withstand the earth force behind it, because now we've got metres of pile length sitting on some solid ground, and all that earth's pushing on it. A bridge does what we call cross-propping. So you sit it on the bank on the north side and on the south side, and when you go across it, the ground on either side props it from one side to the other.
Yeah.
If that ground decides to move, there's got to be something there to restrain the structure.
And the hill that we're on is actually, in a way, trying to push the bridge's foundations as well, isn't it? It wants to fall out.
Well, that's clearly happening. I mean, that has a 4 metre drop down there that's probably somewhere near a 75-degree angle. And when it gets down about 4 metres, you see a definite little shelf there. We're obviously changing our structure there to probably something more hard brown. And then below that, we could be into some greywacke.
So basically, there does not appear to be a lot holding up the bridge. If we remember back to the Good Bridge, Stewart said he would have expected the PS1 engineer to have had a geotechnical report done so that he knew what he was building on. John Scarry. Now, in terms of the PS1, I'm going to get you to design a bridge for me. Presumably, you would want to know what the ground was like that was going to support the bridge, especially given that the bridge itself is 14 metres in the air and is in a wee valley. Is that fair to say, as the engineer?
Yes. Normally, you get structural engineers can do some of their own geotechnical engineering. Generally, you would engage a specialist geotechnical engineer to advise on that.
So basically, it would be very surprising if you as a PS1 engineer had not actually been out and had a geotechnical report done of the ground that was essentially going to be supporting your future bridge.
But again, and particularly nowadays, people would tend to get a geotech engineer to provide some advice and confirmation.
Yeah, and so is it surprising to you that in terms of the Collmog Bridge, I'm looking at as you'll be aware, Peter Bolton was brought before an IPN's disciplinary committee, and as a part of that report, they basically said, this is under the investigative committee decision dated 24th of July 2012, and it says, under the section Bridge Foundations and Abutment Stability, and I quote, Mr. Bolton has not provided any material to indicate an investigation was carried out prior to his site visit on the 1st of April 1997. And then when we look at the first site visit document for that day, it says, on site 4 p.m. to check reinforcing bridge trusses in place, excavation for abutments done, and reinforcing place. So if I'm not mistaken, it seems to me that he hasn't had any geotechnical report done at all, and he's visited the site and basically they've already put the bridge in. So as an engineer yourself, I'm assuming that the procedure that Mr. Bolton followed wouldn't be one that you would follow or expect any other competent engineer to follow. In terms of our bridge, in our location, the 21 metre span, etc.
No, you would normally want to know what you were building it onto.
An integral part of the foundations and the abutments of the bridge is the concrete used to essentially hold it all in place.
We're at the abutment end here, and the concrete, this bridge was never ever set on this abutment. Somebody's propped it up on a timber block to get it into its position, and then they have just put some corrugated iron up against the end of it and dumped concrete down over it. And there's concrete all over the metalwork. It's just an absolute mess.
So, for example, over here, this is a bit that's intrigued me. There seems to be a beam of wood or something there.
That is wood. What they've done is when they've dragged these across here or whatever, they've propped them up and got them into the height they want so they're in alignment with each other and blocked them up with a block of wood, and then they've just dumped concrete over the top of them.
Now, I'm not an engineer by any means, but it strikes me that perhaps you wouldn't want to put wood inside concrete.
No, I mean, the correct way to do this job would be to bore down and put your foundation piles in first. Once you've concreted those up, you may actually box the whole abutment in one thing and put your cages in, tie them into your cage at the top of the abutment work and pour the whole thing at once. Otherwise, you'd pour the piles and then you'd box around those, put all your abutment steel in, position your anchors, box and pour that off, and then you'd crane your bridge in. Having put the bridge in, you'd normally finish one abutment first, completely head wall and everything, crane the structure in, and then you can put an expansion joint into the back end and pour the last head wall after.
Now, correct me if I'm wrong, but it almost looks to me, judging by the way the steel from the bridge is coming out of the concrete, it's almost as if they placed the bridge down and then almost buried the end in concrete, for want of a better word. Is that...
It's very clear that what they've done is placed the bridge to where they want it, blocked it up to suit, and then they've just mixed up concrete and thrown it over the top.
And the concrete that they've used, it almost looks like there's several different types, is that right?
There are multiple different batches of concrete in this foundation.
And is that a standard practice?
Absolutely not. I doubt whether some of that would come to 10 MPa, which is what we call site concrete for filling in holes. It is certainly not structural concrete.
And does concrete in this kind of application need any kind of metal or rebar reinforcing?
Yes, concrete is only good in compression. The moment you get any movement, you need steelwork in it to take the tensional forces. Clearly, this concrete now is compromised because the ground has moved from under there. Any movement on this and that whole truss there, that concrete abutment's coming into tension on the top face, the steelwork should be coming into play.
Is there any indication to you, because we're looking at areas where they've removed concrete, I can't see anything that would indicate any kind of rebar.
I highly suspect there is no rebar in here from what I've seen.
So just to go back a minute, basically this concrete work, or a certain portion of it, would have been put in before the steel structure was here?
No.
Would have been done in one go?
In the normal situation, this concrete abutment would have been poured and finished.
And inspected.
And have your bearing pads and everything all set up ready before these trusses get craned into position.
So going back to my original question that I did for the steelwork, has at any point in this bridge's life the abutment at the southern end or the abutment at the other end been fit for purpose?
No, never.
Have at any time in this bridge's life, have they ever been safe?
No, they've never been safe. There's been no geotechnical investigation done. Had it been done, they would never have allowed that type of construction.
And so we're not talking about something that was originally safe and it's deteriorated over time. These were never safe.
They were never safe.
Ever safe. Okay.
Never, ever safe.
So looking at the concrete, and again, I'm not a bridge builder, but is there anything, I think it's easier if we just say, is there anything good about it?
No.
Now would be a good time to speak with our engineer, John, to try and understand what is going on. Okay, now looking at the abutments of the bridge, one thing that I noticed when I photographed this bridge quite a lot, and that is that there are definitely several different types of concrete in the abutment. Is that normal?
Well, no. If it's I think on that bridge it's an L-shaped abutment.
Yes, it is.
And one, you would normally then expect two concrete pours. One would be for the slabs that the bridge sits on, and the other one would be for the wing wall, which basically goes vertically and keeps the soil back and supports the road as you drive onto the bridge. So, but one, and given the size of it, one would one would expect each abutment to be in 2 pours, and you would probably pour both of the flat sections at the same time on opposite sides, and then the 2 walls. But with proper formwork and compaction, one would normally expect it to look fairly monolithic.
So as a layman, I wouldn't be able to go there and then say, oh, there are 3 different types of concrete.
No, you shouldn't. And if it's properly compacted and so on, it'll probably have a bit of a rough finish being the sort of structure it is, but it should look fairly monolithic.
So you wouldn't expect to see large, like 3/4-inch pebbles in there?
Well, if you can see individual stones, it indicates that the concrete has not been properly compacted.
Yeah, you can definitely see individual stones. And look, the other thing that's interesting is that in the site, I went there, and I'm absolutely not a structural engineer. I have no structural engineering experience whatsoever. But when I was photographing it, there are actually wooden beams embedded in the concrete, and that immediately, to me as a layman, struck me as very strange. And then I went back and listened to the IPEN's inquiry, and there's a section in there where Mr. Bolton essentially says that when he turned up one day, the bridge was jacked up on top of something, and they were pouring concrete into the underside. And so it immediately leads one to assume that they'd basically dug out, excavated the foundations, they'd put big wooden beams there, put the bridge on top, and then basically just poured lots of concrete in. And when you look at it, that's exactly what they've done, because the wooden beams are there in the concrete's all over the metal structure. And the interesting thing was, though, in the IPEN's inquiry, one of the people there actually said, was that normal procedure? It seemed to strike him as a little strange. And Mr. Bolton basically turned around and said that as far as he was concerned, there was nothing odd about it. Long story short, that strikes even me as being very odd. Is that a normal practice? Is that something that you would do, to basically prop something up on some wooden beams and then bury it in concrete?
No, the normal procedure, those trusses, whether they're reused from off-site or brand new construction, they're effectively off-site.
Yeah.
You would normally not bring them until your abutments had been completed, and then you would lift the truss in to sit on the abutment.
So by that, you basically mean the abutment concrete should have been poured and was completely dry before the trusses even arrived?
Yes. Concrete hardens under a chemical process, so it can do it underwater. But basically, you would, just to give you room to do the wing wall, you would cast the slab and the wall and then let it harden for sufficient time that it could support just the weight of the truss. So you'd probably wait 7 days or something, and then you would bring a crane in or whatever, and then lift the trusses in, presumably to be attached to some anchor bolts which had been cast into the abutments, precisely located using templates and surveyed to accuracy.
Now,
if you were to put the... if you were repairing a bridge in situ, you might jack something up, but you would do a much more professional job of it.
You would, wouldn't you? You wouldn't just use wooden beams. To
repair concrete underneath.
Yeah.
But also, if you've got a couple of large pieces of timber dunnage that the truss has been sitting on, and then you just sort of pour in between them, well, I would be most surprised if the concrete was not designed to be reinforced in both directions. So it holds together and can spread the load.
So suffice to say, this was wrong.
If the timber cuts through, where's the reinforcing?
Yeah, exactly. So basically, it's safe for me to say that what was done was wrong. It should never have been done.
Well, it sounds like it, and again, it sounds like it. If it was a major problem, why not just say it's not like the Auckland Harbour Bridge clip-ons where you have to live with the problems which were put into its original design and construction.
Yeah.
I think you'd have to say, well, why don't we start again?
Well, that's the thing, and I was actually going to bring in the council inspectors later on, but given the fact that I, as a layperson, you can't help but miss it. And there's a lot of the concrete's actually been eroded away over the years, along with a lot of the bank. But if you went back to 1998 when the council inspector went to inspect the bridge, Again, I'm not a council inspector, but I should have thought that if you went under the bridge and looked, presumably if you had even the slightest knowledge about construction, you should have been fairly confident in seeing something wrong. I mean, I can't imagine that they would have said, oh, that's fine.
Yes, and I mean, it might be a small bridge, but it does have to carry, presumably, trucks.
Yeah, it does, because they wanted to build a house on the other side.
Yeah, and, the trucks will have heavy loads on them, and you're talking large forces, and there might be thousands of little bridges around, but they're all presumably designed properly to support those loads.
So basically the council inspector, if he had seen nothing else, he should have at least seen that.
Yes, I would say that even if he was if he was remotely involved with the building control department of the council, then it would have at least raised alarm bells to bring in someone, even if it was an external independent consultant.
The next part Stuart and I looked at was the steelwork which makes up the main trusses and structure of the bridge.
I see a couple of latticework truss frames that were, in a previous life, some form of overhead gantry.
That's a crane, or what is that?
That's a mobile structure used for lifting articles in a yard or a building.
So it's like a big gantry crane.
Yep, that's exactly what it was.
Yes, you heard correctly. The Bad Bridge is made up of 2 gantry crane trusses that originally resided in a concrete yard in Otaki. Now, you know why we had to use second-hand steel for our good bridge in Part 1.
The state of the members in it, being the bottom chords, the diagonal braces, the transoms, the bents, they have such severe corrosion on them to the point where, in some cases, they're not even there. They're completely rotted away.
Okay, so now let's look at the members themselves. Now, this is a truss crane, so it's basically a box, and I'm looking at the beams underneath, and a lot of them are bent. Now, if I'm correct, there are 2 ways that they could become bent. One would be through stress in the actual lifetime of the bridge, and then the second way would be for them to have been damaged before the bridge was actually erected. So, from what you can see now, which of those 2 do you think it is?
From the bends that we have in these members, it is clear to me that these bends have occurred dragging these trusses over the ground. How you identify that is the south end that we're sitting at has significant damage to multiple members, all in the same direction. If you go to the north end, there's next to no damage there, because that's the end that was picked up and dragged.
So essentially this end that we're sitting in was in contact with the ground for a greater period of time.
Scuffing down the road.
And tell me, if you were to see damage like this in a new bridge before it received the PS4, would you have expected a PS4 to have been issued?
Absolutely not. It would have been condemned.
And would you have expected the engineer that is supposed to compile a PS4 to have mentioned these as defects?
Absolutely. He would have ordered that they be removed and replaced.
So when you see this, and we're looking at a bridge that's been erected for, 15 years? How did this happen? How did this get here? How was it that, for example, in the PS1, my engineer should have specified the structure, and the PS2, another engineer should have checked that. Then in the PS4, in the PS3, the person constructing it should presumably... Would it have been reasonable to expect that the person constructing the bridge would have noticed these areas of damage and reported them?
I suspect that the person constructing the bridge did the damage to these.
And so, having done it, should they have reported it?
Absolutely.
And did they?
To the best of my knowledge, no.
An important thing to keep in mind is that the physical damage to the steel was not the only issue. The coatings also get damaged when it is dragged along the ground. Mick Morris. If you'd seen someone dragging your fresh coating across the ground, what would you do?
I'd cry a lot.
And presumably...
It's a terrible thing to do to it.
And as you, as a professional, and this has been a theme with this bridge, if you saw that happening to a structure, presumably you would be duty-bound to report it.
Absolutely. I mean, the idea of the coating is to be a barrier on the surface to protect it against corrosion. That's the aim of having the coating there. If you've damaged it putting it in, it needs to be repaired.
And needless to say, one would have thought that Mr. Bolton, being the PS1 engineer for the bridge, and having seen the bridge in its installed position, would have at least noticed the damage and certainly should have ensured that the contractor repaired the damage. Sadly, none of these things happened, and what is more, the council inspector also didn't notice the damage. John Scurry. Now, I'm assuming that as the PS1 engineer, and for that matter probably the council inspector, first of all, it would be reasonable to expect that you would pick up that kind of damage to a corrosion prevention coating. Would that be correct?
Yes. If you are the design engineer, you should keep in mind essentially how something is going to be handled and built. One of the things that is... Just talking about buildings for a moment.
Yeah.
One of the things that has annoyed me enormously in New Zealand is often the paint systems you specify on exposed steelwork, say some columns in a foyer or whatever, they can be extremely expensive three-coat systems, and yet that steel will be painted with this pristine finish, and it will be thrown on the back of a truck and other bits of steel thrown on top of it, and lifted with chains and the paint system damaged. And I insist on, I put in my specifications, if a proper paint system like that is applied in the shop, I say that the paint must be allowed to harden.
Yeah.
You must lift it with soft straps. You must have timber dunnage and soft packing in between. So
it sounds to me, as the PS1 engineer, you're actually responsible for, first of all, specifying the kind of corrosion protection coating that needs to be applied.
Yeah. With a bridge like that, with those trusses, one would normally expect them to be called up to be abrasive blast cleaned and either a hot zinc spray put onto them or what's called an inorganic zinc silicate.
Yeah.
And that might just be enough to protect it, but you would expect the contractor to then handle it in a way that he didn't destroy it. And even if you had galvanising, you can't just drag the thing along the road. And if you were going to drag the thing along the road, one would think that you would then insist that the contractor put wooden sleds sort of strapped on or something to minimise the damage to the truss.
Yeah, no, he didn't.
And then when you turned up on site as the observing engineer and you saw all of the stuff had been stripped off, then you would insist on repairs in situ if they could get to it, or lift the truss up and fix it.
Well, you see, it's interesting because on the 10th of February 1998, the bridge engineer has the second site inspection report, and basically in it he says, bridge construction complete. And he says here, which again is quite interesting, it says inspection reveals 1, soil build-up around the steelwork at buttress has to be removed. 2, stormwater at each abutment has been, etc., drainage basically. And then 3, ask to check bridge deck fixings. Now, presumably, number 4 on the list should have been do something about the foundations, and number 5 probably would have been something along the lines of straighten out all the horribly bent members on the bottom of the bridge and then reapply the coatings. But they don't seem to be here. Does that make sense to you?
Well, you see, one of the things too with a truss is those individual pieces which act together to form this deep compound beam. They're essentially within sort of fabric rolling and construction tolerances. They're supposed to be straight. unless you've specifically designed a member to have a kink. You don't normally design to have a member to have a kink in it between those node points.
So it's safe to say that for a truss, it's actually very important that if it's designed as a straight edge, it should be a straight edge.
Yes, and particularly if the member is compression. If you've bashed a member so that it's got a big bow in it, then its strength and compression will be far less than if it didn't have that big bow in it. And if it's in tension and it's got a big bow in it, well, it would make it far more flexible. Basically, they're supposed to be straight members, and the contractor is supposed to handle it in a way that it goes up and it's straight.
So far, we have looked at the mechanical problems with the metalwork. Well, I'm afraid, as the old TV saying goes...
But wait, there's more.
What else is there about the steel? So, for example, I'm looking down here and it's almost as if someone has actually bitten a chunk out of this. It's basically an L section, so it's like a corner, and it's as if someone has bitten a chunk out of it. Now, tell me about that, because when we were talking before, you were telling me that if there was a washer missing or a nut missing, the engineer had to do, or would be at the very least expected to do, a defect report. And we're looking at a beam that has a whole chunk missing.
Yes, and I think you'll find if you check Peter Bolton's original design, he makes mention of pieces that have had gas cut. That's had a piece gas cut out of it. Something was possibly welded to it in its former life as a gantry, and it was cut off, and they obviously weren't considering reusing it. Whoever bought these to use them as the bridge, the consultant has said these need to be rectified. They have to be cut out and repaired and then blasted and painted, and the work has clearly never ever been done.
So if you as a bridge builder, if somebody did that to you, or you found that in one of your bridges, presumably you would be beside yourself. Just this little chunk, never mind all of the bent beams, the rusts, the fact that the things probably should have been condemned before it was even built.
That is a bottom chord, and that is a tension member, and you've just removed 40% of it.
So that's really bad.
That's really bad.
So to put that in perspective, that's like having a person hang from a cord, and the person weighs 100 kilos and the cord can carry 100 kilos and there's a big chasm underneath them, and you just take 40 kilos of strength away from the cord and hope it will hold.
That's correct.
So looking at the condition of this metalwork as it is now in March of 2015, and assuming that no preventative rust treatment or no intermediate rust treatment has been done, is it possible that when the bridge was constructed that there was no visible corrosion on it, no rust?
Absolutely not. This corrosion's been here for 20 years or more.
It is not possible to overstate the terrible condition that the steelwork of this bridge is in. And even as a layman, I have very little trouble believing that on the day the bridge was installed, there must have been some rust visible. But I am not a corrosion expert. Luckily for us, Mick Morris is, and he has seen the pictures of the bridge. This is an example of debris being stuck in a crevice, isn't it?
Yeah,
and then,
back-to-back members, angle-line.
And take me through what's happened in that to that section. What has happened? Because it looks like it's almost like someone put a little balloon in between the two members and just pumped it up and pushed them apart.
Yeah, it's significant crevice corrosion. And unfortunately, that's a design flaw as much as anything.
And does this go back to when I was asking you before about if I was designing a bridge in an area where I knew there was going to be debris, you probably wouldn't want to create crevices like this where stuff could accumulate.
Exactly.
Looking at this picture, and again, this is DSC 1342, the damage where the steel is actually missing, would it have been possible from a coating standpoint, let alone just from a plain looking at steel standpoint, would there have been any signs of damage there when the bridge was installed 17 years ago?
Almost certainly, assuming the bridge is in the environment that you're describing.
Yeah.
Because the deterioration of the member that's in the photograph we're looking at, DSC 1342, is such that it's physically impossible in the absence of any other intrusive elements.
And the intrusive elements would be something like salt, air.
Ordinarily, yes. Sometimes though, stray current and those sorts of things is relevant, but from what you tell me, this is in the bush with nothing around it.
And there are no electrical cables going through it or over it anywhere near
straight
it.
current's almost,
it's
highly unlikely. But looking at that in answer to your question, for it to have deteriorated to the extent that I can see clean through it, over a period of 17 years, says to me that it had significant corrosion at the time in which it was installed, and it was poorly protected.
So again, we're moving to another picture, and this is DSC 1345. And in here, I think I'm just looking at it, and again, I appreciate the fact that we're not at the bridge, but I can see what looks to me as a layman to be some kind of red coating, and what's more, it's in a way protected from the elements, but the members underneath just seem to have absolutely no kind of coating at all.
Yeah, there's
or maybe white.
There has been some, what I think's a primer on that, and there's very little of it left. There's significant rust as well as pitting.
And missing chunks.
And there are bits of the angle line gone completely.
So looking at this picture, could you imagine that 17 years ago when the bridge was built, that the steel that we're looking at right now in DSC 1345 was brand new, and an engineer looking at it would have approved it as being suitable for purpose?
In the environment described, no, I can't believe that'd be the case, because it simply couldn't have deteriorated this much in that amount of time.
Yeah. See, the two members that we're looking at now were actually parts of a derrick crane at the Stresscrete Yard in Otaki.
Before they were
turned into a bridge, yeah.
Most that accumulation, Jack, that you were asking about.
Yes, okay. So this is DSC 1350, yeah. And so we've basically got these. Now this looks like it's still got primer on it, doesn't it?
Yes, it does. Yeah, and that was probably in reasonably good condition
17 years ago.
17 years ago, but that this in turn is further evidence of what you've been asking about. If that primer is still in reasonable condition, and again I'm looking at a photograph, I haven't been to the bridge, etc., it says to me that the fact that the rest of the structure is in such poor condition means that in the absence of any other influencing factors like salt and those sorts of things that we ordinarily look for, it wasn't in good condition when it went there, not only in terms of what coating may have been on the surface.
Oh, I see, yes.
Exactly, because I mean, quite simply, you're looking at a coating that I've got to guess because I can't see the coating, but a coating that probably wasn't meant to do anything other than be under a top coat.
Yeah.
Protecting steel for 17 years in this particular environment with reasonable success. Those portions of those members
have done well.
Look quite okay.
Yeah.
However, there's significant rust directly below it.
And that's where stuff's been accumulating.
So it couldn't have, logically speaking, it couldn't have been in particularly good condition in terms of its protection from corrosion at the time that the bridge was actually put into place.
And the other thing I suppose to note is that if there was more than one coating of protective material applied to the bridge when it was made, in the natural course of the protection degrading over time, presumably you would start to see different colours as the different layers became visible. Is
Ordinarily,
that
earlier in the conversation we talked about the nature of a high-build system, the fact that we have a zinc primer, which is grey because zinc's grey, on the surface that we're going to protect initially.
So this has probably not had zinc applied to it, do you think?
I think that what we're looking at there is a primer.
And a primer is just paint. It's not a zinc treatment.
It could be anything, and without testing
again,
it.
Yes, of course.
Exactly, but it might be a red lead primer.
Yeah.
I'm not sure. But whatever it is, it appears to me to be a primer, and it hasn't had any build coats put over.
Except a thick layer of debris. See, again, we're looking in this picture underneath the decking surface on DSC 1353, and to me as a layman, I can see red paint. Now, the impression that I'm getting from you is that this poor layer of primer that was applied perhaps when the bridge was new has pretty much been just left to fight the battle all by itself.
It looks to me to have done a fairly good job in most cases, which is why I suspect it may contain lead.
So again, we're looking at DSC 1355, and you can see here we've got what seems to be intact red paint or primer with perhaps a splash of yellow.
Yeah, I don't know what happened there. But if you think of it, these surfaces are allowed to drain.
Yes, and so the paint's reasonably intact.
Exactly, which in turn means that there's very little debris collects on them. Whatever rain and things gets under there washes them off. However, when you get down to these crevices and areas where debris collects, there's something there to hold the moisture. The moisture contains the oxygen, the steel contains the iron oxides rust. Look at it.
And we can actually see some leaves poking into the right-hand side of the picture.
Just add a bit to it. It's a lovely moist area, I can see that.
Yeah, it's brilliant.
Yeah.
So we're looking down, this is Bridge 15th March 2015, frame 6, and we're looking right down the side of the bridge. And again, just as a layperson, it looks to me like there might be some red paint, which again seems quite well protected because it's at the apex of the truss. But as you were saying before, down the bottom,
where the debris is collected, you've got corrosion, which is what you'd expect.
And once again, we're looking at 15th of March, frame 9. And again, this portion here, which I'm blowing up, again, there are two pieces of steel on either side. And if we look at the steel behind it, there are actually bits of...
Back-to-back angle line again, the intention being to put sufficient steel in there for the structure to do what it was intended to do, but the crevice between the two collects debris. The debris collects moisture. The moisture promotes corrosion.
And then this is the underside of the...
What a mess. Heavens above.
So this is Bridge 15 March 2015, frame 14. And to me, even to me, it looks terrible. And from what Stuart Quigley was telling me, he suspects that the cause of these bent members that I'm pointing to you now was the fact that when the bridge was installed, it was essentially dragged across the ground and they were just bent.
Yes.
Now, forget structural integrity, forget whether it is dangerous to the rigidity of the bridge, just purely as someone who applies coatings to things. If you had seen...
Coating would be ruined.
Yeah, exactly. If you'd seen someone dragging your fresh coating across the ground, what would you do?
I'd cry a lot.
And presumably...
It's a terrible thing to do to it.
And as you, as a professional, and this has been a theme with this bridge, if you saw that happening to a structure, presumably you would be duty-bound to report it, as in you would issue a defect notice saying that the coating was no longer viable because it had been damaged.
Well, I'm not sure what the regulations are here, but
just as a professional...
Absolutely. The idea of the coating is to be a barrier on the surface to protect it against corrosion. That's the aim of having the coating there. If you've damaged it putting it in, then it needs to be repaired.
And so you as a person who does this for a living, and as a company that does it for a living, forget government regulations. You would professionally, just out of pride for what you do, would compel you to have something done about it.
Yes, of course.
Yeah.
You wouldn't take a car out of the showroom with a dent in it or a big scratch in its paintwork. If you've got a problem like that, you need to rectify it.
Let alone crash it into a pole.
Exactly, and roll over a few times. Which looks like
but again, as we were saying before, the upper parts actually look... There's more red on them to me.
Yeah, there's what
so the deck's protected them.
Remains of the coating system.
Again, so this is a section here that I've paid particular attention to, and we looked at this in an earlier photograph. This is a load-bearing member, obviously, and this is where the metal's accumulated. So looking at picture, Bridge 15 March 2015, frame 26. Now, I'm not an expert, but there's a large chunk of metal missing. But there's also what appears to be a pile of almost, for want of a better word, maybe soil or silt or something on there.
Yeah, well, that upright member's corroded through completely. You can see daylight through it. And there is an accumulation of something resembling dirt.
That would probably hold moisture in some form.
Well, certainly hold moisture and promote corrosion, whatever it is.
So essentially
it looks like powdered concrete. to me, but I mean...
Yeah, and this was formerly in a concrete yard.
I see, yeah.
Actually, now there we go. That's another thing. Again, you're the coating specialist, and I come to you and say, I've got this, what was a gantry crane in an old concrete yard. I'm assuming it's not unreasonable to expect that you would be rather annoyed if there were actual patches of concrete still on the steel when you were asked to apply a coating to it.
You need to remove them.
Yeah, so there's just no way that would be acceptable no matter what the coating system.
No, the whole surface needs to be prepared properly.
Yeah.
And in particular, when it's a zinc that's going onto the steel, you want the two elements to be in touch. So you don't want any contaminants
to get in between
the
them
zinc from the steel.
So looking at this particular section in more detail, so this is a ruler here, which is about 10 millimeters. So the steel I've measured it is 10 millimeters thick. And we're looking at frame 15 March 28. Now this again is this, to me, it looks like paper mache. Or, no, it actually looks like puff pastry because you've got so many different layers. So what's happening in there? Why is that steel suddenly...
crevice corrosion, and it's occurring for the reasons that we've discussed.
And how does that actually physically work, though? So something gets stuck in there and a little bit of corrosion starts. But this looks like there are almost a dozen different individual layers.
It's just crevice corrosion manifesting.
Yeah.
That's how it'll always appear.
Okay.
It's a very powerful process too, Jack. The corrosion won't stop occurring, so the expansion won't stop either. So not only are you losing steel and therefore structural integrity, the expansion which is being brought about by the corrosion occurring is damaging the structure. It can, for instance, break fasteners and things. If the expansion goes too far, they stretch too far and break.
Right. So basically in this situation whereby you've essentially got two vertical pieces of steel that are about 15 or 20 millimeters apart from each other, not only do you have the corrosion weakening the inside, but the steel that's still intact on the outside is actually being pushed outwards by the corrosion. So it's almost as if you've got a car jacking between these two members and started jacking them apart.
That's what's happening.
On top of the corrosion.
Yeah. Crevice corrosion can be seen in these sorts of circumstances right down to where mating surfaces have corrosion's begun to occur between mating surfaces. You were saying that there was about a 15 mil gap there.
Yeah, yeah.
Well, this is a welded structure, so you're not going to see it on this ordinarily. But if it were bolted or some of the old riveted structures, if corrosion happens to commence between the two pieces that are bolted or riveted together, then the bolt or rivet
would just pop out.
Exactly. It won't handle it. Usually it corrodes as well as it happens, but it won't handle it.
And this is a zoom in of that previous shot. And so we're looking at Bridge 15 March 2015 0031. Again, for me, there's no way that steel could have been in usable condition 17 years ago when the bridge was built.
Assuming the environment's as benign as you describe it, there's severe corrosion beyond pitting to the point where we can see clean through the member.
The member, yeah. Now, it's interesting you should say pitting because, again, so this is on the underside of the bridge, under the deck, and this appears to be maybe a yellowish... It almost looks like, if I had to say it, it would look to me like someone put orange spray paint on top of the red.
My guess is that it's the deterioration of the
paint.
That was there. I was going to say primer. I don't know that it's a primer.
Yeah. But there seems to be only one layer of whatever it is.
There does seem to be. I mean, the fact that the main coating there is red and what we're looking at's yellow suggests that at some point it had a yellow coat over it, but it's the lack of evidence of it across what I've seen of the whole structure so far says to me that this is possibly something that's isolated, and it might even be to do with the deterioration of the coating and staining from the rust or similar.
And that's frame 33 on the 15th. And then another one is this section here. So this is essentially...
What section, Jack? There's nothing left here.
Yeah. And this struck me as quite extraordinary as well because I'm fairly certain that the original thickness of that steel was about 10 millimetres. And this is, if you imagine an I-beam, so the letter I, we're essentially looking at the left top edge of the eye. And it's, again, like pastry. But it's not sandwiched. So how does that effect happen? I think I have a better photograph of it.
It's just corrosion taking its course.
We'll talk about these later
look
on.
at the pitting. That's quite extraordinary. I'm beginning to wonder about the nature of the steel, frankly.
Well, yeah, for the purpose of this documentary, from what I've been told, for bridges you would use standard steel.
For bridges, yes.
Yeah, there doesn't seem to be anything particularly extravagant about a bridge.
For some other structures, you use different forms of steel. Transmission towers have special steel.
Okay.
And you've said that this was
a former truss crane.
Yes.
So it's a derrick crane. Basically, It was up and these are the derricks off the crane.
It's a question for someone other than me, but there's a case to ask the question because special steel could well have been used. And it, in turn, may have a different corrosion characteristic.
And in general, if it was a specialised steel for something like a derrick crane, presumably it would be, a higher temper or...
Yeah, high tensile steel of some kind has probably been used, but again, I'm out of my depth with that.
Yeah, no, that's fine.
That's a question.
So there is a question as to
the nature of the steel. I mean, is it necessarily appropriate to use a crane, something that was put together?
Not this one, anyway.
Exactly. Intended to be used as a crane as a bridge. I don't know. Perhaps it is. Perhaps they're excellent.
See, there's a measurement. That's 10 millimetre thick. That's a close-up of a section. And again, this that we're looking here, this is frame 48. Let's say that it was used... Okay, let's do it this way. If this was a different steel, say a steel for a crane, presumably there wouldn't be that huge a difference from the standpoint of the corrosion. And if anything, I should have thought that if it was a higher quality steel, does that necessarily mean that it might be less susceptible to corrosion, or is that wrong?
The amount of carbon in the steel is relevant, but there's no one-size-fits-all answer to that question. The different steels will perform differently. Remember at the start of the conversation we talked about Osten and Corten steel?
Yeah, we did.
Yeah.
And so from a coatings perspective, is it fair to say complete disaster?
Absolutely. Although I don't think we should hold coatings in too poor a regard because it seems to me there was very little coating on it when it went in there.
Yeah, it's again, just as a layman, as I said earlier on, when I looked at the bridge from the surface, I thought it was all right, but then as soon as you get underneath, it's like,
Yep. I mean, with council and government bridges, there's a regular inspection regime, etc. With a privately owned bridge, people don't
do it.
I would think get under there. Mate.
Now we're looking at this. Remember, we had the vertical section, and there was the pitting at the bottom. It was split apart, and there was a hole in it.
Yep.
Now this is a picture. This is frame number 53, and the thickness of that original steel was about 5 millimeters. Because I've got a ruler here, and the gap was 15, or no, slightly less than 15 millimeters. So it was about 5 millimeters steel. And again, this is frame 54. What does that do to your heart?
Well, there's been a lot of accumulation of debris there and consequent corrosion, and a lot of the steel's gone.
In fact, it almost looks like the part of the accumulation at the bottom is actually the steel came from the top.
Yeah. I'm wondering what this stuff is, but yeah.
And it looks like, the spiderweb soil. So, okay, so basically, in terms of corrosion and the coatings that are used to protect it, one of the biggest enemies, aside from the elements themselves, are these accelerator items that get onto the coating and essentially magnify the effect of the environment.
Yeah, well, ordinarily the most significant effect they're having is holding moisture, as I've explained before.
And that's what this is doing.
Well, it can be that there are other things that are collected there as well. If, for instance, there was stock passing over the bridge, there could be urine and things that come from the stock, which in turn will accelerate it. But basically, you're just looking at a lot of debris collection areas that hold moisture and promote corrosion. Yeah.
Who can look at it and tell me what's happening, because the thing is, these are not subtle things.
It's rusting, Jack.
Yeah, it's rusting. There's your problem.
Yeah.
So it's not a matter of a subtlety. It's essentially, it's basically falling to pieces.
I mean, your common sense will tell you a number of things about it. And you've pointed them out to me, not the other way around. You've said to me, look, there's coating intact there. It's intact. We can't change that.
Yeah.
It's intact.
Yeah.
What does that tell you about the areas of corrosion?
Yeah.
Well, except for the fact that there's debris accumulation typically in the areas that have corroded, it tells me that it's not a particularly aggressive environment that it's in.
Yes.
What was there in the first place has been sufficient to protect it for this period. So that, in a general sense...
So basically what you're saying is that because it seems that originally a simple base coat was applied, and the fact that base coat has, in probably quite a substantial amount of the bridge, actually, when you look at it from the outside, has managed to survive to the point whereby you can still see it over the last 17 years.
Well intact, in fact.
Yeah. Would indicate that the environment is not that aggressive.
Exactly, yeah.
So that then means that to have sustained the level of corrosion that it has, even in areas where there aren't necessarily large amounts of debris accumulation, the steel must have been in fairly bad condition, and by bad condition I mean probably some rust.
In terms of its coating, yes. Because it's
when it was first installed.
Well, it's typically rusted in areas where you'd anticipate that it would. Those are debris collection areas. Yeah. The fact that it's rusted there is not extraordinary. All bridges will do that when the coating system finally breaks down. My point is that the coating system, which appears to me to be inadequate for the purpose, remains intact in other areas. So the environment itself is not particularly aggressive.
Yeah.
Therefore, it was perhaps not in particularly good condition when it went into service. If it were in good condition, and if all else is equal and there's nothing else that we don't know, then the bridge would still be in reasonably good nick now. Those areas where the debris collection has occurred 17 years, by now you'd probably be starting to have a bit of a problem. Because but
when you say a bit of a problem, we're not the kind of problem that we've got here.
Similar to that. The coating itself would perhaps by now be breaking down. I've got to keep this in generalities.
Yes, of course,
17 years, different environment, blah, blah, blah. But just the very fact that you've got some relatively intact coating by the look of the photographs and some other areas of extreme corrosion says to me that the other areas of extreme corrosion were already like that, and not like they are today. They'd already begun.
At the time it was new.
The coating system was probably gone.
So just looking at one of the areas where the coating system seems to have survived, and survived quite well, and this is 15th March 2015, frame 38 onwards, we're looking at this metal and there's pitting in it, but the coating seems to be intact.
It's been applied over the
pitting.
Yeah.
So I've got another one here we're looking at, and it's probably at least a good 3 millimeters deep into this steel member, and the coating is in the hole. So the coating was painted over the hole.
Well, assuming it hasn't been painted since, then that was how it was when it went there.
Well, actually, no, that's good that you bring that up. So from what you've seen, and obviously you haven't been to the bridge, you haven't seen every square inch of the whole thing, but is there anything that you have seen that would give you any indication that any kind of painting or coating had been applied since the bridge was installed?
No, it's exactly the opposite. I'd be quite... I'd be astounded, in fact, if it's been painted since it's been in there.
Yeah, so it's safe to say in terms of this frame 40 on March the 15th that the paint that we're looking at is actually the original base coat or whatever it was that was applied.
I'd be confident that that was there in 1998.
Along with the holes.
Along with the holes. They didn't appear since because the coating's intact.
Yeah, and again, this section here, you can see the coating's intact on 43. So to summarise, having seen the pictures that I've given to you and your experiences since 1995 with numerous bridges, how does this bridge make you feel?
It's extraordinary. It's quite negatively stimulating. I hate to see it, frankly, but it's an example of the sorts of things that are out there. And this is what happens if you don't get the coating system right in the first place. Specify the right system, prepare the surface properly, put the coating on correctly, and make sure that that's how it is when the structure's left.
And you, as a coating professional, what would your comment be on the performance of the people that applied the coatings to this bridge?
Well, they probably did it quite well, because I think when that was done, it wasn't a bridge. I don't think there's been, from everything you've shown me, I can't say to you, Jack, that there's been any painting done to this structure since it's been a bridge, or even probably prior to that. It seems to me that it's probably a crane that's been taken out of service and just put in to be used as a bridge. I don't think it's had any attention at all.
So basically, there's a possibility. I mean, we can't confirm it, but it sounds to me, and now that I think about it, I think you're probably right, that this was originally installed as a derrick crane at a concrete yard some years before it became a bridge, and essentially it went straight from there to being a bridge, and there was no paint or corrosion protection done from then to now.
That's how it seems to me. You've shown me nothing that tells me that it's had any attention at all.
So again, if you were someone working on a project like that, you would pick that up, wouldn't you? You would notice that.
To me, and I repeat, I'm not an engineer. To me,
but just as a coating specialist.
Well, it has too much pitting to have gone into service.
Yeah.
I think, you need to ask an engineer, I think that some of those pitted members would have needed to have been replaced, and this is prior to any consideration of coating the structure so that it won't corrode. You've got members in there now. You showed me one with severe pitting.
Pitting in the steel,
and the coating's still intact, which means that unless it's been painted since the structure went into place, that pitting was there when it went into place.
When it was a crane.
Which in turn means that, if I'm correct in my guess, and I stress it's a guess, this is a job for someone with different qualifications to me, it was too pitted to have gone into service in the first place. I mean, this appears to me to have had no coatings attention at all. And as it happens, you're able to show me a frame there that shows significant crevice corrosion, but with paint over it. And so if it hasn't been put there since the structure went into place,
that means it's always
obviously it was always there.
And the thing is, you were mentioning, okay, now let's explore that point you've just made. First of all, what is pitting? What is it? Pitting, crevice corrosion. What is that? Not crevice. Pit, this one here. What we're looking at now.
That's pitting.
Yeah. What's pitting? How does that work?
Well, we've looked at rust in various circumstances.
Because this is a vertical member.
That's correct. We've looked quite a lot at crevice corrosion, which is rust in a crevice. Pitting, for the sake of this discussion, is rust in a hole. That's all it is. It's no different.
And it almost like it burrows in.
Yeah, for the sake of this discussion, it's rust in a hole. There's more to each of those forms of rust than meets the eye. Normal patches of rust are to some extent compounded by the remaining coating because they're exposed and the rest of the surface is not. Pitting, crevice corrosion varies with the size of the crevice. I said to you that in some cases they're mating pieces. There was intended to be no gap between them, and the ones you've been showing me has a significant gap. There are other things that affect crevice corrosion, but for the purposes of this discussion, they're not that relevant. The pitting. The pitting that you're showing me is significant, and it means that the steel that used to be there isn't anymore. And in the case of the frame that you're just bringing up,
this is frame number 40 on the 15th of March 2015.
There's significant pitting with intact coating inside the pit.
So the pit, basically this severely damaged steel was coated with a protective layer.
Exactly, and I mean, heaven knows when, but given what I've seen of the rest of the structure, it wasn't since it went there. I've no way of knowing that. Perhaps someone went in there and coated the pits. Fairly unlikely, but it could have happened.
As a layman, it's almost like you've just smashed up your car, and the way you're going to fix it is by painting it.
Wow,
because that steel looks pretty damaged. Because to me, that steel looks pretty bad.
The bog has fallen out.
Yeah,
right.
Exactly.
The bloke before you told you'd been driven by a little old lady and never had an accident.
Yeah,
and in fact, you've run into something and you've found all the filler has just fallen out of the ground. It had an accident. It had been repaired. In the case of this, though, it's exactly that. The pitting's quite obvious. The difference in the case of the bridge and the hypothetical car that we just spoke about is that they didn't put any bog in there.
I realise that some of you may think we have spent an inordinate amount of time looking at the steelwork and its corrosion. There is a good reason for this. It is very difficult to understand how it could have been possible for the steel on the bridge to be in brand new, fully and properly rust-free and corrosion-protected condition on the 10th of February 1998, the day the second site inspection was completed by Mr. Bolton. It was on this day that Mr. Bolton wrote on the top of his site report/instruction form, and I quote, "Bridge construction complete." None of the major problems we have not only heard about, but actually seen are mentioned on the site report. Next, Stuart and I looked at the underside of the road surface. Okay, so now the next bit of the bridge. So in a way, the first part of the bridge is the abutment, the second part is the steel structure. Now we're looking at the road surface from underneath, because I suspect before we go to the top, you're going to have a fair bit to say about that. How important is the road surface? And this is the surface that the trucks and the cars go along.
The road surface is critical to the vehicles on top, and does play, if it's installed correctly, does play an integral part in the bridge. You can increase the depth of the cords by putting sufficient anchorage in there and gaining further compressional depth out of it. You won't get anything out of this thing. It's not tied down properly. It's got 2 bolts every metre. The rest of the boards are just floating there.
So basically what we're looking at are what look like, if I wasn't mistaken, they're like railway sleeves, almost that kind of size.
Yeah, they're Pinus radiata. It's low-grade timber. They're 140 millimetres by 200 millimetres, and they do not meet code.
And so most of them are lying on the surface, and then every once in a while there's one that's actually bolted down.
That's right. Every 5th or 6th board is bolted down, and it is bolted down with a couple of 12mm
bolts. And one thing for me that I'm just looking at, if you can imagine, there are the 2 main structural lines going out on the left and the right outer edges, and then there are 2 other ones on the inside. So it's almost like there are 2 box sections going down. And it seems to me that neither of the sections in the middle are actually in contact with any of the boards.
That's right. What they've done is they've just thrown the boards on top of the gantry rails.
So these are the rails on either side, on the outside?
They are the rails that your little bogie runs along to carry your crane assembly. And the timber is only bearing on those points and has got 45mm gap between that and the inner truss face.
So should they be supported in the middle? I mean,
it should have been supported there, and that would have made the deck capable of withstanding the wheel loads that it has to.
So am I correct in saying that basically all of the load that is transmitted from the deck onto this bridge is actually only being transferred to the 2 outer edges?
That is correct.
The 2 mid edges are basically doing nothing.
That's correct.
And that's not a good idea?
No, I mean, the truss, that's the whole thing. The way this truss was designed, it was designed to put the load into that, but as a bridge, the interfaces should have been beefed up, and then it should have been packed to the deck, and then you could have transferred all that extra load down into that other truss member.
And the other thing is that the left one seems to be about twice the separation from the surface as the right-hand one.
Yeah, well, that's what happens when you start blocking things up with blocks of wood and you don't quite get them right and you're not worried.
This raises another issue with the bad bridge. The span of the bridge in reality is about 21.5 metres, but on the original specification and in the PS1 calculations, it was stated as being 16 metres. Thus, the calculations used in the initial design were actually wrong.
The span the consultant has used, given to him by the developer, was 16.5 metres. These trusses are 21.5 metres. that's 5 metres shorter. The span is 5 metres shorter than the overall truss length. When you take a structure and you double its length, the structure needs to be 4 times stronger to carry the same load.
And this is not the only problem with the design calculations done for the bridge. John Scarry.
I was made aware of was problems in defining what the actual truck loading to be used was.
Yeah.
There wasn't a clear statement as to what vehicle the bridge was to be designed for. But I have seen computer input and output from a computer analysis for the bridge, and I do not have a user manual for that program, but they all have similar attributes, and it appears to me that instead of the bridge itself, the trusses span from one end to the other end. They are supported right at their very ends on abutments, and then the rest is an open space over the stream or river.
Yeah.
But it appears, my memory is that a mistake was made in the analysis and some supports were put into the computer model along the span, which weren't there in reality. So the forces in the bridge that were designed for did not represent the actual actions one would expect under the stated design loads.
And so basically the bridge was at no time ever actually capable of supporting the load that it was in theory designed for?
Well, I don't know. I mean, the simple fact is that the design didn't match reality.
Finally, Stuart and I came up to the top side of the bridge, and the first thing that strikes us is a 2-inch gap between the road and the start of the bridge. And then we looked at the railings. Now, there's a step here where there's concrete and there's the wooden part of the bridge.
Yep.
But there's about a 2-inch gap. Is presumably, again...
That deck's been pulled up and moved. It may never have had that gap. It may have always been there. I don't know. It looks like that gap has been there for a considerable time.
And there's corrugated iron.
Yep. So they've not boxed it off in a professional-like manner where they've had a straight line and been able to marry their deck up to the abutment.
And so looking along, we've got the rails. So obviously the surface is important. What about the rails?
The rails are extremely important to all pedestrians. When you're putting in a bridge, you have to establish its use. In a rural zone, is it being used for traffic? Are people walking across it? Are they likely to walk across it? Are people biking across it? Are they riding horses across it? The manual changes for each of those. So
for our bridge here...
You do not have to have a handrail if it's only ever trafficked.
Okay, but this one's not.
That's right. So where you have pedestrians, it's at that time the requirement was for a rail to be 900 high if there was more than a metre drop.
And so at the centre of the bridge, we're 14 or 15 metres above the river?
14 metre drop.
So the thing to think about this is that it's not just pedestrians or cars. If you can imagine someone walking across and a car comes across and you were surprised and you wanted to get out of the way, it's conceivable you could actually hit the barrier quite hard because you were jumping out of the way.
That's right.
So this barrier here on this bridge, describe it for me.
This barrier here consists of 4x3 tannalised posts with their restraining face being the 3-inch depth.
And they look like they're nailed in.
They've been nailed into the deck timber with a bolt going through the curb, and then they have a single bolt through each rail with a 5x2 top rail and a 6x2 mid rail.
So in your experience of having built 100 bridges over more than 20 years, is this a good rail?
This rail never ever complied to code. The spacings are too big. The maximum gap you're allowed between the rail is 300 millimetres. This exceeds that.
So a person could actually conceivably slip down through the rails quite happily.
That's
Wouldn't
correct.
be hard.
Not hard at all.
And so, again, I'm going back to our usual question, have the rails ever been in the lifetime of the bridge
Never.
fit for purpose?
Well, no, see, this is what we call a general type rail, where it is a post and rail. At the 5 metre mark, I said before that when a bridge hits the 5 metre possibility fall, it all changes. This rail is illegal in this situation.
So here's the thing for me. All of the other things that we've talked about up to now have been engineering things. They've been things like rust, paint, structural stuff. That this, on the other hand, is pretty obvious. It's just wrong. So should, at some point, this have stopped the process?
If the inspector from the council knew anything about the bridge manual, he would have known, walking up to this bridge, those curbs will never ever meet code, and those rails cannot be used in this situation.
So the way I see it, there are two possibilities. One is that the rails were never here when the bridge inspector came, because the other scenario is that they are so obvious that I would assume even the most incompetent engineer who even professed to have the minimalist knowledge of bridge, this would be... You would have to be blind. You couldn't see it.
Don't dare say that about blind people, all right? If I brought a blind man out here and I'd explained to him the code, he could identify these as non-compliant.
Whereas the people that inspected this bridge... I mean, what I'm getting at is this should have stopped them in their tracks. Forget everything else.
Absolutely.
If they never went under the bridge and if they never saw everything else, this should have stopped them.
One look at this is, sorry guys, that does not comply to code. Remove those wheel restraints, remove those rails. I want to see code compliant material there.
And so Gary would never have been legally allowed to use the bridge with the rails the way they are.
Absolutely not.
So once again, how did that happen?
Well...
It is hardly surprising that a fair proportion of the people who come into contact with this bridge end up speechless at one time or another. And let us not forget, so far we have been listening to this program for 1.5 hours. Gary and Lynn have been stuck with this bridge for 17 years. Inspections. We are now reaching the end of our journey, and this leads us to probably the most important and worrying aspect of all, inspections. Over the last 1.5 hours, it should have become clear that the bad bridge has had major problems going right back to the very beginning. And one of the most troubling aspects of this story has been that no one picked them up, not the design engineer, not the contractor, not the customer, and not the council. Yes, some issues were picked up, but in the big scheme of things, they simply pale in comparison to the ones that were not picked up. Thus it seems logical that to understand what went wrong, the best course of action would be to try and work through the correct procedure and attempt to identify the problems as they arose along the way, and then look at how they were missed. You will recall from part 1 that when we built the good bridge, a set of procedures had to be followed, and as part of those procedures there were several layers of checks and inspections. To summarise the proper procedure that we followed for the good bridge, first you need to confirm that a bridge is actually needed. Second, you need to obtain a resource consent. Third, you need to engage a competent design engineer with experience in bridge design. Fourth, your engineer should then determine what the nature of the bridge is to be. Fifth, the engineer should visit the site and obtain a geotechnical report so that they know for sure what they will be building upon. Sixth, the engineer would then design the bridge using the New Zealand Bridge Manual as a standard. This becomes the PS1. Seventh, the engineer would then have the design checked by a second engineer who would look for errors in the original design. This is the PS2. Eighth, before any construction can begin, a building consent must be obtained from the council. Ninth, a suitably qualified contractor would then be engaged either by the customer or by the PS1 engineer to undertake the construction of the bridge. This is the PS3 stage. During the construction phase, we've heard that there are probably at least 4 or 5 minimum inspections that should be done by the PS1 engineer. Unless they are aware, these are being completed by another competent engineer. In the Bad Bridges case, Mr. Bolton was the only engineer, and he completed 2 site visits only, the second and final one of which occurred once the bridge construction had been completed. Further, it is the responsibility of the contractor to bring any defects or other issues to the attention of the PS1 engineer in writing, so that the engineer then has a chance to make a determination on how the problem should be rectified, and then to confirm that those rectifications have indeed taken place. 10th, the PS3 is signed by the contractor, stating they have completed the construction diligently, competently, and to the original PS1 engineer's design. 11th, the original PS1 engineer is to go to the site and inspect the finished bridge to confirm that it complies with their original design, that it complies with the relevant standards, and that it has been built in a competent manner and is safe to use. Once they are convinced that all of the above is indeed the case, they sign the PS4. 12th, the PS4 is then presented to the council, and they in turn dispatch a building inspector to the site, whose job it is to inspect the bridge and confirm that it has been built according to the PS1 engineer's design, complies with the relevant standards, has been built in a competent manner, and is safe to use. They also have the duty to point out any defects that need to be remedied before they can declare the bridge fit for use. Should the bridge pass all of the above, the council will issue the bridge's code compliance certificate, which says that the bridge is safe to use. And finally, after all of that, Gary and Lynn can use the bridge to get to their property. Well, sadly, Gary and Lynn cannot get to their property 17 years after the bridge was issued its code compliance certificate, which said they could. Well, we had better crack on then. Step 1. Confirm a bridge is needed. In Gary and Lynn's case, access to their property is via a gully about 20 metres wide and 15 metres above a stream, and the gully below is strewn with rocks. So yes, we need a bridge. 2. Obtain a resource consent. A resource consent was obtained for the Bad Bridge, and it is interesting to note, at the very beginning, the regional council should be aware of the fact that someone has a desire to put a bridge across a gap.
Absolutely.
3. Engage a competent design engineer with experience in bridge design. Looking at the design certificate for the Bad Bridge, dated 3rd of April 1997, it states that the design engineer was Mr. Peter Bolton from Base Consulting Engineers Limited. In 2012, Gary and Lynn took a case against Mr. Bolton to the Institute of Professional Engineers New Zealand. During the course of the proceedings, Mr. Bolton states the following. So we know for a fact that at the time Mr. Bolton designed the Bad Bridge, he had no prior experience in bridge design. And remember, Gary and Lynn did not own the bridge and had nothing whatsoever to do with its design or construction. Mr. Bolton was engaged by the landowner, a Mr. Moffat. John Scary. Is the council under any kind of obligation to actually confirm that the person, the PS1 engineer, is actually even qualified to do it?
Well, strictly speaking, theoretically, anyone can still come along and design a structure other than a house. But in reality, nowadays, you effectively need to have a chartered professional engineer in charge of the design and signing it off or in peer reviewing it. But again, an enthusiastic amateur could do a design. It would be up to the council to check that the actual design was competent.
Well, it's interesting you mention that because I'm looking at a document which was done, it actually attached to the original design certificate, and it is called the Guidance on Use of Producer Statements. And there's a section down towards the middle, and it basically says definition of suitably qualified design professional. And it says a suitably qualified design professional should have recognised qualifications and experience for the work undertaken, and should be either, and then it goes on to list a number of organisations.
Yes.
4. Determine the type of bridge required. This is more to do with the materials used to build the bridge and the type of bridge itself.
Years ago, it came around that nobody looks under a bridge, and steel deteriorates. So it's a dangerous medium to use for a farmer. In the situation where you're dealing with a transit bridge or a council bridge, every bridge is inspected every 6 years.
If you were building a bridge on a private property or a farm, is it not really that good an idea to use steel?
It's not a good idea at all, because the layman bridge owner, if you will, with respect, probably believes that he's made the right choice of material and he can forget about it. But that's not the case at all. Steel's going to rust if the coating system, as all coating systems will,
eventually
deteriorates and it's exposed to the environment.
It would appear that Mr. Bolton's decision to allow Mr. Moffat to use the second-hand crane trusses from the concrete yard was ill-advised, and given the private nature of the bridge, reinforced concrete would have been a better choice. 5. Visit the site and get a geotechnical report. Once again, referring to the IPEN's hearing, a document titled Investigating Committee Decision regarding the complaint brought by Gary and Lynn Hurtanon about Mr. Peter Bolton, MIPENZ, dated the 24th of July 2012. And inside this document, in section 9.2, under Bridge Foundations and Abutment Stability, the report says, and I quote, Mr. Bolton has not provided any material to indicate an investigation was carried out prior to his site visit on the 1st of April 1997. And looking at Mr. Bolton's site report / instruction sheet dated the 1st of the 4th 1997, it states, on site 4 p.m. to check reinforcing, bridge trusses in place, excavation for abutments dug, reinforcing placed. And then there are some notes underneath. The thing to keep in mind is that no geotechnical report was done for the bridge's site. John Scary. If I'm not mistaken, it seems to me that he hasn't had any geotechnical report done at all, and he's visited the site and basically they've already put the bridge in.
For a small bridge, you might say such and such a bearing strength required to be confirmed on site. And obviously you want to be bearing onto soil which is not going to be easily eroded from underneath your abutment. But it's a bit late if the bridge is largely in paste to be trying to check your bearing.
So as an engineer yourself, I'm assuming that the procedure that Mr. Bolton followed wouldn't be one that you would follow.
No, you would normally want to know what you were building it onto.
So tell me, what is holding this bridge up? What is actually holding us up?
The grace of God at the moment, because there's nothing much under that foundation there. The bank has crumbled, and when you look under there, there is fractured brown rock, which realistically a slight earth tremor could cause a whole lot to go.
Design the bridge. As we learned in Part 1, the New Zealand Bridge Manual is the basis for bridge design in New Zealand, and more importantly, it is the basis for bridge design in the Building Code. Looking at the original design certificate for the bridge, there is a section into which the engineer is to enter the relevant building standards. The New Zealand Bridge Manual does not appear there. John Scary. It's not unreasonable to expect that when the council was presented with a PS1 and they knew that it was for a bridge, they would expect to see under the list of standards the New Zealand Bridge Manual.
Yes, and also, again, for a producer statement, for a bridge, one might think they would check to see if the person actually had designed bridges before.
It is also at this point that the materials for the bridge were chosen. The customer had presented the design engineer with a former truss crane from a concrete yard and asked him to use it as the structure for the new bridge. We are already familiar with the various defects in the steelwork, so we won't repeat them here. John Scurry. And the Collmog bridge has 4 trusses, doesn't it?
Yes, they were apparently reused off a crane out of a precast factory or something like that.
Now, if you were the PS1 engineer, and again, this is a common sense kind of question, but if I came to you and you were my PS1 engineer and I said that I'd wanted to make a bridge over a 20-metre span and that I wanted to use a second-hand crane from a concrete yard, would you have then felt an obligation to actually go and check the steelwork and have a look at the structure?
Yes, using a truss like that for a bridge is problematic, I think the correct word is, because a truss is really designed to have loads put at the node points where the members meet. That's how it's most efficient. One of the problems with a bridge, if you're not having a purpose-designed truss, is what is the effect of the wheel loads when they're between the points, the main points or main nodes of the truss, because that induces secondary bending moments. Now you can allow for that, but if any sort of reused steel work, you need to know what condition the steel is. Is it rusting or whatever?
Yep.
You would also be interested to know what the quality of the original construction was, and also what the members are. Often, if something's been up for 20, 30, 40 years and it's worked well, one of the problems will still be a person will not have any drawings for it, and it can be an extremely difficult process of site measuring the truss, so you know what to draw, know what to analyse, and know how to modify.
So it's safe to say that you as a PS1 engineer would first of all want to go and see the truss?
Oh, definitely. Unless you had some very good drawings for it,
yeah,
you'd still want to know what condition.
But even if you had the best drawings on the planet, you'd really want to go and see it personally, wouldn't you? Because at the end of the day, you're signing on the dotted line.
Yes. It would be unusual to take some trusses which were for a completely different type of structure. 7.
Have the design checked, PS2. This is one of the first checks designed to try and catch mistakes. John Scurry.
I have seen a computer input and output from a computer analysis for the bridge, and I do not have a user manual for that program, but they all have similar attributes, and it appears to me that instead of the bridge itself, the trusses span from one end to the other end. They are supported right at their very ends on abutments, and then the rest is an open space over the stream or river. But it appears, my memory is that some mistake was made in the analysis, and some supports were put into the computer model along the span, which weren't there in reality. So the forces in the bridge that were designed for did not represent the actual actions one would expect under the stated design loads.
And so basically the bridge was at no time ever actually capable of supporting the load that it was in theory designed for?
Well, I don't know. I mean, the simple fact is that the design didn't match reality.
Referring back to the IPENS report, errors were detected but not removed from the drawings used to build the bridge. 8. Obtain a building consent. We have heard previously that a building consent is required before construction is allowed to begin. For the Bad Bridge, the building consent was issued on the 21st of April 1998, which is fine. The only problem is that according to Mr. Bolton's site report dated the 10th of February 1998, the bridge had already been completed. So now the question becomes, what happens if you do not have a building consent? So what happens if I don't get a building consent and I just go ahead and build it?
You would be running an extreme risk. The if the council found out about it, well, irrespective of whether you get a building consent, there is a requirement that under the Building Act, all building work, whether it requires a consent or not, must comply with the building code. In other words, it's got to work. If you go ahead and do a design and do some construction without getting a building consent, several things can happen. You run the risk of the structure being torn down by the council, being ordered to be torn down. You also run the risk of being disciplined for not working in accordance with good professional or trade standards.
And then you also mentioned the fact that in the event that you construct something without a building consent, and if the council was to find out, it's well within their rights for them to instruct you or to have the offending building demolished.
Yes. If it was a building and there were no planning issues involved, they may read the Riot Act and then allow the structure to be assessed, but generally they're well within their rights to demand that illegal construction is demolished.
And that's the same for a bridge?
Yes, and you also have other practicalities too. If you do an unauthorised extension to your factory and your factory burns down, I would be most surprised if your insurance company didn't say, well, that work was unlawful or contributed to it and we're not paying out.
In the case of the Hurtnons Bridge, the original building consent was actually issued after the bridge was finished, and initially the council, it seems, were quite upset. So at that point, presumably it would be reasonable to expect the council to be doubly cautious, having become aware of the fact that something such as a bridge, and especially with the span, has been built without any kind of building consent.
The first alarm bell that should be ringing is if there's no building consent, what is the quality of the work? And the nature of that bridge being some reused trusses, etc.
Yeah.
You would want, I mean, it just, to me, not an experienced bridge engineer, but as a structure, it didn't look right. And you would want to be particularly careful.
9. Find a qualified contractor to build the bridge. For the bad bridge, one thing that stands out is that no one actually seems to know who built the bridge. Yes, no one knows who built it. From what I've been told by John and others, it is highly unlikely that the design engineer would not know who constructed the bridge. As the design engineer, if you're doing site inspections, is it reasonable to expect that you would know who the contractor was that was building the bridge?
As the engineer, you may not be involved in any of the contractual aspects.
Yeah.
But you invariably have to write down something in writing to get some remedial action done. You know, there's always something that needs to be done. And normally, the normal form is you say to the, and you name the contractor. You really need to know who the contractor is. It's so obvious.
So going back to this first site report inspection of the Collmog Bridge on the 1st of the 4th, 1997, you're right. He's actually got notes here, and it says addition of HB bolt, each end needed. There's basically a list of things that need to be done. So he would then have to have known whom it was that was doing the work.
Well, yes, and also you should have a knowledgeable builder, a competent person doing the work, and normally that is going to be a commercial operation. Now, you might have, in special circumstances, the owner who was putting the bridge, the person who was putting the bridge in, might have had a mate who was a retired ex-army engineer who knew how to put bridges up properly, who was doing it. But someone doing the work should be knowledgeable and know what they're doing. And normally it will be a commercial contracting firm which knows how to do basic building work properly.
So if you as the PS1 engineer was to know that the person doing the construction had actually no qualifications whatsoever to be doing it, what would you do?
Well, you can account for that if you know that is the situation. For example, I worked a little while up in New Guinea where the workforce is generally poorly skilled, and you compensate for that by having people who know what they're doing stand over them all the time.
Yeah, make sure they do the job, yeah. Once again, in order to gain more of an insight into the issue of who built the bad bridge, we need to turn to the IPENS hearing for Mr. Bolton.
It's always trusses came from a precast yard, so it was a bit of a different sort of job. He wanted the job done. He saw it as an economic way of getting a bridge built. So from that point of view, he did a lot of work himself, which is a bit of an issue. There were some other drawings that were supposed to be done, which were done by somebody else, so there was a bit of an issue there, but I don't have any problems with them.
So the pre-assembly of this bridge was shown, from what we've heard, that it was trucked into the site and craned in. Was that done by Mr. Moffat or some other engineering company? I couldn't tell you. Okay.
But just further to that, Mr. Bolton, you said that Mr. Moffat did some of the work himself. Can you tell us a bit more about that from what you remember?
Well, my brief was to provide the design for the bridge structure and the abutments. I excluded the head rail. I excluded the site drawings for it. I had no knowledge of him being a builder, but I had no way of that knowing whether he was going to use a builder or do it himself. So my brief was to provide the design and at the end of the day do supervision for it.
In many ways, the last section is the most telling. When Mr. Bolton is asked to elaborate on Mr. Moffat's involvement in the construction, he says several interesting things. First of all, Mr. Bolton did not know if Mr. Moffat was qualified to construct the bridge. Second, Mr. Bolton earlier states that Mr. Moffat wanted the job done cheaply, and hence Mr. Moffat did a lot of the work himself. He even goes on to state that this was a bit of an issue. Thirdly, when asked if the pre-assembly of the bridge was done by Mr. Moffat or by some other engineering company, Mr. Bolton's reply was, "I couldn't tell you." And finally, Mr. Bolton says, and I quote, "My brief was to try and design and at the end of the day do supervision." This tells us it is not unreasonable to conclude that Mr. Moffat did some or all of the construction of the bridge. The lack of a reference to any other construction party supports this. It is not possible to comment on any construction qualifications Mr. Moffat may or may not have had. Having said that, and assuming we accept that Mr. Moffat played even a small role in the bridge's construction, the level of competence demonstrated in the bridge's construction provides some guidance on this point. In terms of the design engineer's supervision of the construction process, Mr. Bolton has stated as much above. Thus, if he was supervising in any way, we can be guided by what we have heard earlier, that it is not unreasonable for him to have known whom constructed the bridge. 10. PS3 signed by the contractor. Given the items raised in Step 9, it should not be a surprise that there does not appear to be a PS3 document for the bad bridge. 11. PS4 site inspection by the design engineer. Once again, for the bad bridge, we find the IPENS hearings helpful. Let us listen to how Mr. Bolton described the bridge's PS4 at the hearing.
Looking back on the PS4, I accept that I should not have issued a PS4. It was done to satisfy a client. It was the wrong thing to do, and I do apologise for what's transpired has caused some hurt to some of the people.
Mr. Bolton does not try to defend the PS4. He simply says he should never have issued it. As the original design engineer for the bad bridge has admitted that his own PS4 should never have been issued, there is little more to add. 12. Council inspection. Despite all that has occurred up to this point, the 17 years of loss, frustration, extreme financial as well as emotional cost that Gary and Lynn have had to pay, and indeed are still paying, could have been avoided had this last step gone properly. But as with so much about the bad bridge, this final opportunity to produce a good bridge was also lost. As far as I am aware, there is no existing copy of the inspection report that was done by the council inspector. In case you were wondering, yes, the bad bridge did get its final code compliance certificate. In fact, it got two, on the same day, because it is said that the first one was actually signed by the office girl at the council. The second, issued on the same day, is even more intriguing, because according to Gary and Lynn, No one at the council seems to know who signed it. Despite what we have heard, it would be pure speculation to try and say what led the inspector to sign the bridge off as being safe. And in fact, I am yet to see any document that says who the inspector was and what the results of his inspection were. So the most instructional course of action to take at this juncture is to hear from the experts. So as a rough guess, is it reasonable to say that there were probably at the very least 5 clear instances in which the council could reasonably have been expected to stop or at least make some note as to the things that were wrong with this bridge?
Absolutely. The council should have had alarm bells screaming with this bridge.
So there's not reasonable to believe them when they say that it's not their responsibility, they didn't know about it. Could they have ever... Is there any way in which they couldn't have known about it?
It's totally farcical. They took money to inspect the structure. As a regulatory authority, they were required to do due diligence and investigate the design before they issued a building consent.
So I know you weren't here, but this fascinates me. How on earth did this bridge... How did it not happen? How did someone not see something was wrong? From the council, the engineer... It's almost as if you had to have a conspiracy because there are so many points at which, as we've just established, a member of the public could have pointed out things that were wrong.
There's either been a clear case of neglect where nobody has inspected the structure, or, heaven forbid, somebody has paid someone to turn a blind eye.
And it seems to me the only other possible explanation is that someone who was sent to inspect it just didn't know what they were seeing.
No, that couldn't happen. They clearly didn't look.
Yeah. So basically, if a housewife could come and see that there was something amiss, then an engineer should... Okay.
A building inspector, if he looked at it and couldn't see that, he shouldn't have been in his role.
So here's the thing for me. All of the other things that we've talked about up to now have been engineering things. They've been things like rust, paint, structural stuff. That this, on the other hand, is pretty obvious. It's just wrong. So should, at some point, this have stopped the process?
If the inspector from the council knew anything about the bridge manual, he would have known, walking up to this bridge, those curbs will never ever meet code, and those rails cannot be used in this situation.
So the way I see it, there are 2 possibilities. One is that the rails were never here when the bridge inspector came, because the other scenario is that they are so obvious that I would assume even the most incompetent engineer who even professed to have the minimalist knowledge of bridge, this would be... You would have to be blind. You couldn't see it.
Don't dare say that about blind people, all right? If I brought a blind man out here and I'd explained to him the code, he could identify these as non-compliant.
Whereas the people that inspected this bridge... I mean, what I'm getting at is this should have stopped them in their tracks. Forget everything else.
Absolutely.
If they never went under the bridge and if they never saw everything else, this should have stopped them.
One look at this is, sorry guys, that does not comply to code. Remove those wheel restraints, remove those rails. I want to see code compliant material there.
And so Gary would never have been legally allowed to use the bridge with the rails the way they are?
Absolutely not.
So once again, how did that happen?
And
so we're looking at Bridge 15 March 2015 0031. Again, for me, there's no way that steel could have been in usable condition 17 years ago when the bridge was built.
Assuming the environment's as benign as you describe it, there's severe corrosion. Beyond pitting to the point where we can see clean through the
member. Who can look at it and tell me what's happening, because the thing is, these are not subtle things.
It's rusting, Jack.
Yeah, it's rusting. There's your problem.
Yeah.
So it's not a matter of a subtlety. It's basically falling to pieces. Looking at this picture, and again, this is DSC 1342, the damage where the steel is actually missing, would it have been possible from a coating standpoint, let alone just from a plain looking at steel standpoint, would there have been of any signs of damage there when the bridge was installed 17 years ago?
Almost certainly, assuming the bridge is in the environment that you're describing.
Yeah.
Because the deterioration of the member that's in the photograph we're looking at, DSC 1342, is such that it's physically impossible in the absence of any other intrusive elements.
And the intrusive elements would be something like salt, air.
Ordinarily, yes. Sometimes though, stray current and those sorts of things is relevant. But from what you tell me, this is in the bush with nothing around it.
Yeah. And there are no electrical cables going through it or over it anywhere near it.
Stray current's almost.
Yeah.
You know, it's highly unlikely. But looking at that and answer to your question, for it to have deteriorated to the extent that I can see clean through it, over a period of 17 years, says to me that it had significant corrosion at the time in which it was installed, and it was poorly protected.
Yeah, that's pretty much what.
Yeah, I'll say.
But if you went back to 1998 when the council inspector went to inspect the bridge, again, I'm not a council inspector, but I should have thought that if you went under the bridge and looked, presumably if you had even the slightest knowledge about construction, you should have been fairly confident in seeing something wrong. I mean, I can't imagine that they would have said, "Oh, that's fine."
Yes, and I mean, it might be a small bridge, but yes, I would say that even if he was if he was remotely involved with the building control department of the council, then it would have at least raised alarm bells to bring in someone, even if it was an external independent consultant.
Is it? I mean, to me as a layman, I find it rather difficult to understand why all of this didn't happen and why the bridge is still there 17 years later. And I listened to an audio recording of a council meeting recently where Pat Doherty, the CEO, basically said that as far as he was concerned, the council staff had done absolutely nothing wrong. It's almost a question of did they do anything right, in the sense that the inspector didn't inspect it, the PS4 was accepted and it was obviously deficient. A lot of bits of information are missing, and even now the council have had 2 reports produced and both of them say that the bridge was pretty much unserviceable from the beginning, numerous mistakes, etc., and yet it seems the council are saying, well, we didn't do anything wrong. Does that mean that they did everything correctly that they should have done?
And the simple fact, at the end of the day, we have a performance-based code. And basically, we have a bridge which is unsafe to drive on and in a truck, and it was meant to carry trucks, and from day one it was unsafe. Therefore, I don't believe the council could claim that they have done nothing wrong.
A good way to end this program is with an instructive excerpt from a council meeting held on the 9th of May 2013, in which the bad bridge was being discussed by council. The voice you hear is that of Pat Doherty, the CEO of the council.
Yes, there's an assumption here that the council staff made mistakes, and this, I've been involved with this process up until probably about 18 months ago, but it is incredibly complex, convoluted, and long. So we can certainly give you a briefing on the full story, but the assumption that staff have made mistakes through this process, we don't necessarily accept at all.
Finally, I want to make one thing very, very clear. By far, the majority of the staff at the Kapiti Coast Council are hard-working, conscientious, friendly, and take pride in their jobs. In the small way in which I have had contact with council staff, I have without exception been both surprised and heartened by just how much pride they take in their work. The things you have heard in this documentary apply to a very small number of council staff, not to the majority. It would be a great disservice to the council staff and the community in general to in any way take what you have heard as being a general reflection on the men and women working at council.